we already studied about these notations when we have to use. If I write it quickly, big O is for less than or equal to, omega is for greater than or equal to, theta is for equal to, little o is for strictly less than, and little omega is for strictly greater than. Right? So what is this less than or equal to? What is the formal definition of this? Right? If there are two functions f of n and g of n, if there are two functions f of n and g of n, then function f of n can be written as big O of g of n. When can we write this? If and only if there exists a positive constant c and n naught such that f of n is always less than or equal to c into g of n. F of n is always equal to c into g of n. Okay, this way. It means if we see some simple example, 8n cube plus 9n square plus 3n plus 7. This is f of n, assume. Okay, and g of n can be another function. G of n can be another function which such that if I take it as 9n cube plus 7. Only this much is there, 9n cube plus 7. Right. So in this case, f of n is equal to, actually it is equal to. So we say less than or equal to g of n by some multiplication factor, because you have to multiply this with something so that you get this. Okay. So c is such kind of a constant. Right. So f of n less than or equal to g of n, then we have to use big O notation. See the graphical representation here. See, when I am drawing, see there is one function f of n. It's, if I draw that line of that equation, I get something like this. And if I multiply c with g of n, it is always on top. See this point, n naught. Okay, so g of n is always dominating and f of n is small. Right? So I can say n cube. If f of n is n cube, I can say it can be written as order of n cube, or order of n power 4, or order of n power 3.1, which is higher, equal to, or higher than f of n. Okay, this is a kind of a notation we have with us. Right? So this is about big O notation. Then you want to see, let's see small proof that show that 7n plus 1 is big O of n. Let's see this proof and understand whether how, why 7, you understand, right? What is the order of growth of 7n plus 1? It's very clear. Ignore the constants. I hope you remember the rules. Ignore the constants, then ignore the, find out the higher order term. For that higher order term, ignore the coefficients. So it becomes n. It becomes n. Order of growth is n. Okay. So tell me, what is the order of growth of 7n log n plus n square plus 7? What is the order of growth of this 7n log n plus n square plus 7? Can you tell me what is the order of growth of this function? How do you find out order of growth? Right, it is n square, because see, first ignore the constant terms, then ignore the higher order terms. So I have n square n log n. Definitely n square is high compared to n log n. So this I will ignore. If there is any coefficient for this, that also we have to ignore. We don't have anything. So order of growth is n square. So let's see this example. Right? Given function is 7n plus 1 and g of n is given as n. F of n is 7n plus 1 and g of n is given as n. Okay, we need to show that there exist two positive constants c and n naught such that this condition is satisfied. It means if I write here 7n plus 1 is less than or equal to c into n. This is the constant which I have to find out. For all n greater than n naught, for all n greater than equal to n naught. See the definition here. See this very clearly. F of n equal to f of n less than or equal to c into g of n for all n greater than n naught, n greater than n naught. Okay, so here c, we have to do this. So if you put c as 1, so 7n plus 1 less than or equal to c into n. Put c as 1. What will happen? 7n plus 1 less than or equal to 1 into n. So not true for any n naught. This is not true. This is not true always. This is false. Whatever you give n naught value, it is false. Okay, then c equal to 2 if you put, that is 7n plus 1 less than or equal to 2n. This is also not true because 7n is large. So till how long can I go? If I take 7, again it is not true. Why? 7n plus 1 less than or equal to 7n. Here plus 1 is there. 7n, 7 is there, plus 1 is extra. So this is also not true. But when you take for c equal to 8, 7n plus 1 less than or equal to 8n. Right? So in this case, what is happening? This is true. This is holding true for all n greater than or equal to 1. For all n greater than or equal to 1, this is true. Right? Therefore, what is this n greater than or equal to 1 means you put 1 here. This is 7 plus 1, 8 less than or equal to 8 into 1, 8. Satisfied. Put n value as 2. This is 14 plus 1, 15. This is 16. True. Put n value as 3. So on. It is always true. So c value is 8, n value is 1 or n naught value is 1. We have proved that for these two values, 7n plus 1 can be written as order of n. F of n can be expressed as order of g of n. Is it clear? Is it clear? Did you understand this? Let's see the next one. Big omega. Okay, what is big omega function? You can write f of n equal to big omega of g of n if and only if there exists constant c and n naught such that f of n is always greater than or equal to c into g of n. Reverse of big O. Reverse of big O. See the graphical notation, if you see, c into gn is in lower range compared to f of n. Compared to f of n, it is in lower range, right? So if you see this example, I think it's very self-explanatory. Once you understand big O, you will easily understand omega, because this is for less than or equal to, this is for greater than or equal to. Let's see this example. Show that 7n square minus 6n minus 56 can be expressed as big omega of n square. So here, actually speaking, for this problem, if I erase this is true. Okay, this is true. Can I write here equal to big omega of n? Is this true? Like this. I mean to say, is this statement true? 7n square minus 6n minus 56 equal to omega of n. Is it true? Can I write like this? Right? Because, yes. Why? Because this always left hand side should be higher. Okay, always left hand side, the f of n should be large. F of n should be higher only compared to g of n. Then only we use omega. So how do we prove that? How to do that? Again, substitute some values. Take some values for c and verify whether it is true or not. So when I take c as 1, when I take c value as 1, statement is very simple. 7n square minus 6n minus 56 is greater than or equal to 1 into n square. So it is definitely greater than. Why? True for any n greater than 5. Why? Because, see, you put n as 1 here. You put n as 1. This becomes 7 minus 6 minus 5. That is, I think, 1 minus 4. Is it greater than 1? No, it failed. Right? You put n value as 2. Even if you put n value as 2, this will fail. It will pass only for greater than 5. So if you substitute 5 here, then it satisfies this condition. Okay. Similarly, you put C value as 2. Then this is okay for n value greater than 4. Similarly, you put C value 8. It is true for 13. This has been already given. Okay. If you can keep verifying 1, 2, 3, 4, you understand that. Okay. So let's take C as 1 and N naught as 5. Then it is satisfying the condition. So for any C value and N naught value, C and N naught values, this condition is holding. Okay. So sometimes you'll be asked to prove that, show that it is order of n square. So you just do simple trial and error method kind of thing, right? Take C as 1, then C as 2, C as 3, and prove that at C equal to 4 onwards, this is always omega n square. And the third one, theta notation. See, theta notation says that there exist two functions, there exist two constants C1 and C2. There exist two constants C1 and C2 such that C1 into G of n is less than f of n is less than C2 into G of n. It means f of n is in between C1 into G of n and C2 into G of n. F of n is equal to, theta means equal to G of n actually. Theta means it is equal to G of n. Okay, theta notation. So the the definition is, if there exist two constants C1, C2 for which this is satisfied, then we can write it as theta of G of n. So the condition is C1 into G of n less than or equal to f of n less than or equal to C2 into G of n. C1 into G of n less than or equal to f of n less than or equal to C2 dot G of n. Let's see the proof and try to understand what is this example. See, show that n into n minus 1 by 2 is equal to theta of n square. We want to prove this, theta of n square. Okay, so what we have to do? We are given function f of n and g of n. You have to find out two functions C1 and C2. Okay, so if I just expand this like this, you see, n into n square, it becomes n square minus n by 2. That I am writing as 1 by 2 n square minus 1 by 2 n. Okay, this step if you see, 1 by 2 n square minus 1 by 2 n less than or equal to n square by 2. Okay, for all n greater than 0. This is first equation. I have just expanded this. And I have put here 2. Second case, if you see, 1 by n square minus 1 by 2n is always greater than or equal to 1 by n square minus 1 by n into 1 by n. 1 by 2 into n, 1 by 2 into n. Right? So this is also one way. Instead of this, we are having, so we can see that there exists C1 and C2. There exists some C1 and C2s. To make it more simpler, I think here it is going a little complex, but if I take some simple example, let's take only n square. Let us assume our f of n is only n square. Okay, so can I write like this? 1 by 2 into n square is less than or equal to n square is less than or equal to this should be 1 by 4. Right, this can be 1 by 4 here. Let it be 1 by 2 n square. Okay, see, now what is the meaning here? N square is greater than 1 by 4 n square. Right, one more simple example. 1 by 4 n square less than or equal to n square less than or equal to 2n square. See this. So my f of n is n square, my g of n is n square. There exist two constants C1 and C2. There exist two constants C1 and C2 such that this is true. This condition is holding true. Okay. So what is C1 value? 1 by 4. What is C2 value? 2. For these two cases, it is holding true. And n naught begins from 2. N naught should begin from 2. Why? Because if I substitute 1 here, it becomes 1 by 4 less than or equal to 1 less than or equal to 2. Satisfied, right? This example is satisfied. So the C1 value is 1 by 4, C2 value is 2, and N0 value is 1. From 1 onwards, it is satisfying the condition. If you put 2, it again satisfies. Put 3, it satisfies. Then in this case, we can write it as theta of n square. Okay. So this is how we have to prove that no, whether we can write big O or omega or theta. Okay. So again, these are some kind of no small notations. We will just skip this quickly. We don't want to focus more on that. These things we will study with the algorithms directly. I will just quickly go now to our next concept. We are going to see all these things. Our next unit is all about understanding different searching and sorting techniques, and also their time complexity. I'll come to that part. Right? We will see these things. Yeah. Let us begin with our today's concept, that is arrays.